cat person or a dog person? Okay. What else did you put? What did you put, Gigi?
Oh, girl or boy.
Okay, good. So, one, only two possible outcomes. What did you put?
I did like if you like Apple products or not.
Okay. Do you like Apple products or not? A heated topic sometimes. I like that one. Anybody else want to share theirs? All right. So binomial coefficients we'll use those as part of the process of calculating these probabilities. So if n is a positive integer and x is a non-negative integer less than or equal to n, then the binomial coefficient n choose x. We read that n choose x is defined as, so n choose x equals n factorial over x factorial times n minus x factorial. Who recognizes that formula? This is a formula that we've used before. Good. Do you remember what function it was associated with? Combinations or permutations? Remember those guys? Which one? Oh, combinations. You had a 50-50 shot. So that's the same thing as when we were doing n choose x. This is the same exact formula. Remember, order doesn't matter with combinations. And the note says the binomial coefficient n choose x equals the number of possible combinations of x objects from a collection of n objects. If you don't have a graphing calculator yet, you're going to want to grab one. We're going to practice the calculations. So recall that if you have a combination, we actually have a key for that in our calculators under the math menu. Then choose the probability tab and NCR. So we could do 6, choose 1, and we get 6. You'll start to notice some patterns. If we have a 1 as our x value, if we have 6 things and we're only choosing one of them, so if I have these first 2 rows of students, there's 6 of you. If I'm choosing one at a time, there's 6 different ways I could do that, right? So that's always going to be the way that the 1 in the x position works out. 5 choose 3, so you can calculate that. And go ahead and do each of those, B, C, and D. Raise your hand when you've got them all. Good. So we've got 10 for B. What'd you get for part C, Kenzie? And for part D, what'd you get, Shelby? 1. So what would you imagine if I did 12 choose 12? What would the answer be? 1. There's only one way to choose if you're choosing from 12 objects and you want all 12. There's only one combination. So Bernoulli trials. Bernoulli, this is Daniel Bernoulli. There are a variety of Bernoullis. They were all mathematicians. He lived from 1700 to 1792, or 82. Went fast. From Switzerland. And at age 13, he went to college to study philosophy and math. Now, I know in Europe, college is sometimes the level of high school, but regardless, age 13 is pretty young. He was a genius. And so back in the 1700s, he was developing this type of statistics that we're going to talk about today. So Bernoulli trials are repeated trials of an experiment if the following three conditions are satisfied. So the first one, so the experiment, each trial, has exactly two possible outcomes denoted generically S for success or F for failure. You kind of have to disconnect from the emotional response to success and failure, because we might say that, for example, you're an Apple person, Apple product person, or you're not. We might call success being an Apple person. And you might deep down in your gut feel like, no, that's a fail. But for the sake of doing these types of probability scenarios, you got to label something success and something failure. And then two, the trials are independent. The probability of a success, called the success probability, and denoted P, has to remain the same from trial to trial. So like flipping a coin each time, it's a 50-50 chance each time. Probability is 1/2. So the binomial distribution is the probability distribution for the number of successes in a sequence of yes, Bernoulli trials. Got a little video we can watch about him later. It's a pretty riveting documentary. Any volunteers to read about mortality? Thanks, Kenzie.
Mortality tables enable actuaries to obtain the probability that a person at any particular age will live a specific number of years. Insurance companies and others use such probabilities to determine life insurance premiums, retirement pensions, and annuity payments. According to tables provided by the National Center for Health Statistics and Vital Statistics of the United States, a person of age 20 years has about an 80% chance of being alive at age 65. Suppose 3 people of age 20 years are selected at random.
Okay, thanks. The potential career path, being an actuary. So you love doing statistics and calculating certain situations. A lot of potential income in this career path. And it's crazy the way that they can calculate these predictions to help insurance company choose the premiums and these sorts of things. So part A says formulate the process of observing which people are alive at age 65 as a sequence of 3 Bernoulli trials. So we're going to start by naming success. Name our success is 20-year-old, so someone who is currently 20 being alive at 65.
What if you don't want to live to 65?
That's probably one of their factors.
But then wouldn't that make success not being alive at 65?
Oh, you have to disconnect from the emotional attachment to the words, remember? Probability for success, lowercase p, listed here is 80%, so we write that as a decimal, 0.8. And then we're going to also indicate the number of trials, the number of Bernoulli trials. There are how many? 3, yep. 3 Bernoulli trials. Obtain the possible outcomes of the 3 Bernoulli trials. So we're going to go ahead in this question, make a little table. We're not only going to determine the possible outcomes, we're going to actually calculate the probability of each. So here on the left, we'll write out the possible outcomes or the sample space. and then we're going to list out the probabilities. So the first possible outcome would be success, success, success. All three alive at age 65. The reason, just objectively, why I would choose being alive at 65 to be the success, that's also the probability that they gave us was related to being alive, as well as they are asking me questions. Suppose three people, okay, the questions that are following are going to reference being alive. And you could go either way. You could call success being dead by age 65 and saying what would the probability be then? 0.2, 20%. So it'd be the 100% minus, or the 1 minus the 0.8. It actually could go either way. So, but for this situation, we're going to independent events, we multiply those. So 0.8 times 0.8 times 0.8, or 0.8 to the third power. You can calculate that. And then just shout it out. What is it?
51.2%.
Okay. And I'm going to stick with the decimals, 0.512. Then we have success, success, fail. And then we mentioned it, but it's worth noting, the probability of a fail is 1 minus the probability of a success, or 1 minus, I'm just going to go with p, our lowercase p, which is in this case 1 minus 0.8 or 0.2. What'd you get for that one?
0.128.
0.128. And now, because each one of these spots represents a different person, we're going to include SFS as a different circumstance. So 0.8 times 0.2 times 0.8. Doesn't really matter how we arrange those, it's still going to be 0.128. The same number of successes and fails. Then we have fail, success, success. Again, we would have 0.128, same probability. Then if we have 2 fails, need to recalculate that. 0.8 times 0.2 squared, or 0.2 times 0.2. Okay, so we're going to write these as decimals. So how would you write that as a decimal? Good. And then we just rearrange that one. Fail, success, fail, and then fail, fail, success. And those would also be 0.032. And finally, fail, fail, fail. So we're multiplying 0.2 times 0.2 times 0.2 and getting point. Probably could do that one in your head. 0.008. And that is our probability distribution for all possible outcomes. Part C, determine the probability of each outcome in Part B. Another way to do that would be to make a tree diagram. And this is something some people might think that's kind of elementary, tree diagrams, but it is a valid method, frequently used method in statistics, so it helps visualize all the possible outcomes. So we're just going to list this out. Success, fail. Probability of success would be 0.8. Probability of fail would be 0.2. And that would be for our first trial. And then we go to our second trial. Still two outcomes, two possible outcomes. And lastly, our third trial. All right, so once you've got your tree diagram, it makes it a little bit easier to visualize your sample space. So we go SSS, that's one possible outcome. And then SSF. And then we go SFS, SFF, and then down to the lower part of our tree diagram, fail, success, success, FSF, FFS, and FFF. Right, so and then we can list out. The way to calculate those probabilities then is 0.8 times 0.8 times 0.8, which we already know is 0.512. Two successes and a fail is going to be 0.128. And then there's a success and two fails, which is a 0.032. A fail and two successes, back to 0.128. Two fails again is 0.032. And three fails. Listing all these out makes it pretty simple to find the answers to these questions. Find the probability that exactly two of the three people will be alive at age 65. So probability that x equals 2. If our random variable x represents the number of people alive at age 65, then we need to find out, okay, how many different ways can that occur? 3 different ways. So we've got 3 times 0.128. .384. Good. Part E says obtain the probability distribution of the number of people of the three who are alive at age 65. And there's not space to draw that, but this is again linked closely to what we did yesterday, probability distributions. We're going to do the number alive at 65. This is our random variable x, and then these values, there's either 0, 1, 2, or 3 alive at 65. Those are our lowercase letter x's. Those are the value for our random variable. And then our probability of x equals lowercase x will be, so the probability that x equals 0, probability that no one's alive at 65, well, that's our .008. probability that x equals 1, well, we'd have to find out all the ways that that there's just one success. So that's these three right here. So it's the 0.032 times 3. .096. And then the probability that x equals 2, and that's the one that we just did, so it's 0.384. And the probability that all are still around at 65 is 0.512. This is our probability distribution. So we're going to flip the page over here and we're going to see there's actually a way to do this a little more quickly using a formula called the binomial probability formula. So what that looks like is, so we know x denotes the total number of successes in n, lowercase n, Bernoulli trials, with success probability p, all stuff that we just did in the previous question. And then the probability distribution of the random variable x, capital X, is given by this whole thing, which makes more sense when you put in the context. So we'll go ahead and write it out for one that we just did. Probability that x equals 1 in the case of mortality rates. What was the n value in the previous question? How many Bernoulli trials? 3. So it's 3. And our x value is the number of successes, 1. So the probability of getting one success, one person alive at 65, 3 choose 1 times the probability of, so the probability p is 0.8. So the x power, x being the probability of success, so it makes sense. That's the number of times we're going to multiply the probability for success times itself, and then 1 minus p. 1 minus p, what's that? That's just the probability of a fail, right? And that was 0.2. So 0.2 raised to the n minus x, so 3 minus 1 to the second power. On the front, we just did that example of 6 choose 1 was equal to what? If the 1 is down here, then it's just equal to the top number. So just 3. So we're going to have 3 times 0.8 times 0.2 times 0.2. This should look real familiar, right? We just did that. 0.8 times 0.2 times 0.2. And then there's 3 of those. That's where the 3 comes from. So hopefully, having done that first example, you have a little bit of understanding of where all the parts come from. It's not just me throwing a formula at you and going, here, now use it. We should have a little bit of understanding where those elements come from, and then what do we get? Point what? 096. Same as we got in the probability distribution. So let's go ahead and try some out, but first, this box right here I think is really helpful. When you're going about doing questions like this, there's a set of steps. I like steps, especially in questions where there's a long formula. These steps are just going to remind you to write out what is n, what is p, what is identify what you're calling a success. It can be easy to mix up which one's the success and which one's the fail. So it's good to write that down. And of course, we have our Bernoulli assumptions. N trials are performed, 2 possible outcomes. One's a success, one's a fail. All trials are independent, and the success probability, p, has to remain the same the whole time. So let's do some examples. We'll do one with you. N is 3, p is 0.25, and the probability of x equals 1. Probability of one success Our instructions just tell us use the formula and round to 3 decimal places. So we're going to do that. I will say it's a common mistake to put a fraction line here. Do not put a fraction line here. This is not a fraction. So it's 3, choose 1, times our probability, p, 0.25, to the x power, in this case 1, times 1 minus p, or the probability of a fail, which is 1 minus 0.25, which is 0.75, raised to the n minus x power, right? Raised to the n minus x power. 3 minus 1 is 2. I recommend that you're practicing these. If you're entering them in your calculator, it's going to help you become more familiar with doing that. Making sure that you're doing it correctly, comparing your answers. The 3, choose 1? So that's just like, yep, that's the combination. Alright, I'm going to let you guys do these on your own, so you can go ahead and do those next two.